Okay, so the strong form of mathematical induction is very similar to the weak form. It's just that we make a stronger inductive hypothesis. In other words, we assume more when we do our inductive step. And here's what we assume. Remember, for weak induction, what we did was we said, let's assume that the proposition we're trying to prove is true for some k. And now let's prove that it's true for k plus 1, given that it's true for k, right? So we assumed that it was true for some number, and we proved that it was then true for the next number. What we do for strong induction is we say, let's assume that it's true for a certain number and all the ones less than it. And given all of that information as the assumption we're allowed to make, now let's prove it's true for the next number. So in other words, instead of saying, well, it's true for 9, now if it's true for 9, does that necessarily imply that it's true for 10? Instead of doing that, we're going to say, assume it's true for 1 through 9, all those. Now, given that it's true for 1 through 9, all those, is it true for 10? And the same logic applies in the sense that if you prove it's true for the base case, and if you prove that that stronger inductive step is true for all k, meaning if you know it's true for 1 through k, then that implies it's true for k plus 1, then you end up proving it for all integers, right? So here's what it looks like in notation, right? So the strong form of mathematical induction says we need to prove the following two things. Number 1, the base case, so same thing. Prove that it's true for number 1 or for number 0 or for number 21 in the case of our voting and drinking example. Basically the first number that you want to prove it for, right? Prove it explicitly for that one. And then prove that for all I less than or equal to k, prove that P of I implies P of k plus 1. Okay? That's kind of a lot packed in there. So what we're saying is that prove that if it's the case that for all I 1 through k, this thing is true, then that it would necessarily follow that it's true for k plus 1. So if it's true for 1 through 9, then that would imply it's true for 10. If it's true for 1 through 127, that would imply it's true for 128. Okay, so it's just a stronger hypothesis on the left-hand side. And then if we prove all that, then we have proven that for all n, P of n, and really, of course, we mean all n greater than or equal to this number we started with, right, which often is 1 or 0, so it's really all the natural numbers or whatever, right? All right, so let's look at an example here. Remember we talked about free trees. And we said a free tree is a connected cycle with no graphs. So that's one. Isn't that a pretty free tree? And we noted at the time that there's this property that the number of edges is 1 less than the number of nodes. So the number of edges is the number of nodes minus 1. And so in this particular example, we have 7 nodes or 7 vertices, and we have 6 edges, right? And this is how it has to work out to be. Now, at the time, we just sort of said, you know, that's true. But now we're going to prove that it's true. We're going to use the strong form of mathematical induction. I think you'll see why we need the strong form in a minute. So number 1, we're going to do the base case. So note that P of 1 is true. Oh, I haven't stated what the proposition is. Sorry. We're going to say P of n is the proposition that every free tree with n nodes has n minus 1 edges. Okay? So again, we always have to turn mathematical induction into something to do with the natural numbers. So what we're going to put in here is a number, and we're going to say, let's prove that every free tree that has 17 nodes has 16 edges, and every free tree that has 20 nodes has 19 edges, and every free tree that has 100 nodes has 99 edges, right? We're going to prove that every free tree with a certain number of nodes has n minus 1 edges. And of course, we want to prove this for all n. And if we do that, then we've essentially proved this proposition for every free tree, right? Because every free tree has some number of nodes, and that number of nodes is a positive integer. You're never going to find a free tree with -6 nodes. You're never going to find a free tree with 3.1 nodes, right? It's always going to be a positive integer. Therefore, if we can prove this for all positive integers, we've proved it for all free trees. Okay, so first we note that P1 is true, duh, right? If there's a free tree with one node, it has 0 edges. I'll just draw that here for illustration. Isn't that a nice little tree? Okay. All right, back to business. Now, number 2, we're going to make our inductive hypothesis, our inductive assumption. We're going to assume P of K is true, not just for some value K, but for all I less than or equal to K. So we got 3 variables going on here. We got I, K, and N. K is sort of the level that we're at, and we want to prove the next level. I is all the levels up to and including the current level. And then N is the thing that we eventually want to prove for everything, right? So right now, N is kind of off the table. We're just talking about K and I. And we're going to say, assume that all free trees of 17 nodes or less have that number of nodes minus 1 edges. Okay, so all smaller trees than K plus 1, we're assuming that this property holds for. It's a pretty strong assumption, right? And all we have to do is prove that if that's true, then it's true for a free tree with K plus 1 nodes. So we need to prove that P of K plus 1 is true. Okay, so how are we going to do it? Here's how we're going to do it. Take any K plus 1 node free tree. Okay, so the purpose of this step is to prove the proposition for K plus 1. So we're going to say take any free tree of that many nodes. So to make this concrete here, let's just say for a moment that K plus 1 was 6, which means K equals 5, right? So we're saying take a 6 node free tree. Let's draw one. Okay, that's a free tree of K plus 1 nodes, where K plus 1 equals 6, right? Now, what we're going to note is that if we remove any edge in the tree, we get 2 free trees, each with K nodes or less. Now, would you buy that? Let's look at our example over here. If I remove any edge, we're going to get 2 free trees. I think you'll see that's the case, right? Any edge that we remove is going to sever the thing, and it's going to sever it in exactly 2 parts. So if we remove this edge right here, we're going to get these 5 on the outside and the 1 in the middle. If we sever this edge right here, we're going to get these 2 connected and then these 4 connected. Each side is a free tree still, right? And obviously each side is going to have K nodes or less, right? Because we started with K plus 1 nodes, which was 6 in our case. Clearly, no matter how we divide this, each side is going to have 5 or fewer nodes, right? If we remove this one, we have 1 with 5 and 1 with 1. If we remove this one instead, we have 1 with 2 and 1 with 4. We're always going to get something with less than 5 on both sides, right? Okay, now, the sum of the nodes of those 2 free trees is what? K plus 1, right? Because we haven't changed the number of nodes. All we change is the number of edges. Over here, we have 1, 2, 3, 4, 5, 6 nodes. If we sever it right here, we still have 6 nodes. If we sever it here, we still have 6 nodes. If we sever it here, we still have 6 nodes, right? No matter where we pick to sever it, we're going to have the same number of nodes. Okay, so we have we have K plus 1, which is in this case is 6, nodes in the sum of those 2 free trees. Add them both up together, right? Okay, now, let K1 be the number of nodes in the first tree and K2 in the second tree. So we're just defining some variables here, right? We can divide our tree any way we want by removing any edge. And we're saying we'll just call K1 the number of nodes in the first tree, K2 the number of nodes in the second tree. Okay, so how many edges in the first tree that resulted from our severing it here? And the answer is K1 minus 1. How do we know that? We know that by the inductive hypothesis. We are allowed to assume that our every free tree has one less edge than node thing is true for all smaller trees. So since we divided this into two trees, the first tree must have k1 minus 1 edges, and the number in the second tree is going to have k sub 2 minus 1 edges. And again, that is the key gem here, right? That is the thing we are allowed to assume because we're making the inductive hypothesis. Okay, so let's say that's true then. Then how many total edges in our tree? And when I say our tree, I mean our whole one here, the whole one that we started with, right? The answer is going to be k1 minus 1. That's how many edges were in the first tree that we severed, plus k2 minus 1. That's how many were in the second tree that we severed, plus 1. And that's because we removed one edge when we did this, right? We picked one edge and removed it. And then we resulted in two trees that were left, one of which had k1 minus 1 edges, one had k2 minus 1 edges, and then we add all those edges together plus 1. That's how many edges are in our original tree. And I think you'll agree that if you add all that up, that is going to be k minus 1. That means that our original tree must have had k edges, right? Because k1 plus k2 has got to equal k, because the sum of the nodes in those two things, has to equal k plus 1, We started with a tree with k plus 1 nodes, right? So if I take the number of nodes in the first tree and add the number of nodes in the second tree, I'm going to get the number of nodes in the total tree, right? Okay, so then if I take k1 minus 1 edges and add k2 minus 1 edges, and then I add 1 to it, then that is going to end up giving us k1 plus k2 minus 1 plus 1 is minus 1. That's how many edges are going to be in our combined tree. And k1 plus k2 minus 1 is the same as k, because k1 plus k2 equals k plus 1. So k1 plus k2 equals k plus 1. K plus 1 minus 1 is k. Therefore, the tree has k edges. So what we've shown is that if you take any k plus 1 node free tree, it has got k edges in it. So again, come up for air now. A lot of that was algebra and a lot of that was tree stuff. But coming up for air to the mathematical induction thing, we proved that P of 1 was true. And we proved that if it's true that for all I less than or equal to k, P of k is true, in other words, if all smaller trees have one less edge than node, then that whole thing is going to imply that a tree that is k plus 1 in size is going to have one less edge than node. And therefore, those two things together prove that for all n, P of n, in other words, all free trees have one less or one fewer edge than vertex, right? So a lot going on there, and I guess there's two things to get, right? One thing to get is how mathematical induction works, and that's really the big purpose of this episode, right? The second thing is, once you know you're going after this prove the inductive step thing, what are the tricks to do it, right? And that has to do with the particular problem you're dealing with. Are you dealing with, rational numbers? Are you dealing with, in the square root of 2? Are you dealing with free trees? Are you dealing with voting age and stuff, right? I mean, all that is going to totally depend on the problem, and there's, normally some math, some arithmetic, some algebra or whatever to crank through. But the big thing not to lose is that our big strategy was saying, prove it's true for a small tree, prove that if it's true for all trees of this size or smaller, then it is also true for this size tree. And then that ends up proving the whole thing, right? Let's do one more example. We'll get off of trees and go back to numbers here. So here's something you learned at some point in school. For all n, the following thing is true. ab to the n equals a to the n, b to the n. That is a law of exponents, and you can see that's kind of true by saying, what if we have 2 times 3 squared? If I work that out, that's going to be 6 squared, which is 36. prove that that's equal to 2 squared times 3 squared. That's going to be equal to 4 times 9, which, wow, is also 36, right? Seems pretty amazing. It's not really amazing because, remember, a can be broken down into its prime factors. So in this case, 2 and 3 trying to be easy, but let's do a harder example. Let's do 12 times 26, right? So we know that 12 can be broken down into 2 times 2 times 3. And we know that 26 can be broken down into 13 times 2. Those are its prime factors, right? So if I say, what's 12 times 26 to the 4th, that's going to be equal to 2 times 2 times 3 times 13 times 2, times 2 times 2 times 3 times 13 times 2, times 2 times 2 times 3 times 13 times 2, times 2 times 2 times 3 times 13 times 2, right? That's the definition of this to the 4th, because 12 is equal to that, and 26 is equal to that, and so I just multiply them all out like that, right? Well, if you just rearrange the terms, you'll realize that you have 2 times 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 2, right? I'm just putting all of the 2's together, times 3 times 3 times 3 times 3, times 13 times 2 times 13 times 2 times 13 times 2 times 13 times 2, right? And so you're going to end up getting 12 to the 4th times 26 to the 4th just by rearranging the terms, right? Which is exactly what we're trying to prove here, right? Okay, so how do you actually prove this, though? Because that's just an example. So here we're going to say, let's note that P1 is true. And what is P of 1? Well, we're going to say P of n is the proposition that a b to the n equals a to the n b to the n, right? So we're just saying that our proposition is that this does in fact hold for some number n. Okay, so if 1 is n, then obviously this is true because this is ab to the 1, which of course is just ab. And the other side is a to the 1, b to the 1, which of course is just ab, right? So that just trivially works out. In fact, the base case almost always trivially works out. All right, and now for the inductive hypothesis. Assume pk is true. So we assume this is true for some number k. So we're assuming, that is, it's okay to assume that ab to the k equals a to the k, I didn't mean to put that parenthesis there, b to the k. And what we have to do, just to orient ourselves, is prove that ab to the k plus 1 equals a to the k plus 1 times b to the k plus 1, right? So we need to prove that this, if it's true, implies this. Okay, so the way we do that is we crank out algebra. ab to the k plus 1, what is that? Well, that's ab to the k. And again, that's just a property of exponents, right? Remember, 2 to the 8th was simply equal to 2 times 2 to the 7th, right? Because 2 to the 8th, after all, is just 2 times 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 2, 8 times. And so obviously we could take 1 2 out of that and have 2 to the 7th left over, right? So that's just a property of exponents. So we're going to take one AB out of this and put it there. How many ABs will we have multiplying together left? K. Okay, and then just rearrange. Actually, no, not rearrange. We're going to say, we're going to assume that that's this, right? That is the inductive hypothesis right there at work. So we did this basically by just a property of exponents. That's just, in fact, the definition of exponents is how we know that AB to the k plus 1 is AB times AB to the k. This here is a totally unwarranted conclusion. We do not know that this is true, but we're going to assume it's true by the inductive hypothesis, right? That's what we're assuming there. Okay, so assume that's true, then we just rearrange, and now we get, A to the k, or excuse me, A times A to the k times B to the k, right? All I did was swap the position of those two things. And then, lo and behold, A to the k plus 1 equals B to the k plus 1, which is exactly what we set out to prove. So, yay, if we assume that AB to the k is equal to A to the k, B to the k, then it does, in fact, rigorously, logically follow that A to the k plus 1 equals B to the k plus 1. Therefore, p to the n, therefore, p to the n is true. Let me write it better. Therefore, for all n, p of n is true, and our property of exponents turns out to be true. All right, so that's a little taste of mathematical induction. It is a technique that's extremely common in a lot of mathematical proofs, and you will no doubt see it in future classes. And if you haven't seen it yet, you're like, whoa, what are they assuming this, and then inductive hypothesis, and how does that prove the thing? And so you just got to understand sort of the lay of the land. Really very simple chain of reasoning once you get your head around it, but it's a very powerful method of proof. I've enjoyed our time together. I hope you have too. Look forward on this website for future editions of All the Math.